Yes. Can anyone put any lights on this one? Let me repeat the question again. So we solved the last problem using this formula, which is somewhat in between the equation that we got while deriving the equation for the efficiency. But if we try to solve this problem using the final form of the final expression of the efficiency that we have seen, so we need another information, which is YR. YR is what?
So mass fraction of desired material in the reject feed.
Yes, mass fraction of desired material in the reject stream. So how we can get it from this table? Can we get it?
Sir, if we know the input feed and the product feed, then we can use conservation of mass to calculate reject feed, and then we can again use conservation of mass for the desired material to get the mass fraction.
Yeah, so can you check and tell me this value? Like what are the reject here? Reject here is one from the undersize of, now just concentrate on this screen only, right? Concentrate on this screen. This is your this is your product which will come from here. What is the reject here?
Undersize of 20.
Undersize of 20. What is the feed here? Feed to this screen. Feed to this screen is what?
Undersize of 30.
Undersize of 30. Now what you have asked, what we are seeing here, the feed. This is what? This is not this feed. This is this feed. So you cannot calculate based on this feed. So overall your feed is here, and because we are taking this as feed, so we have to take all this reject. So these two are reject. So we take this entire system to be a black box. Whatever going on inside doesn't matter. So we have one input and three outputs. Out of that, one is our product and two is our reject, right? So what are our reject here? One is undersize from this one, and another one, this one, right? Now we have two informations. One is the oversize from 30 mesh screen that we are getting as R1, and we have undersize from 20 mesh screen that we get as R2. Now can we calculate the YR based on these two information? See, you can do it. We know what we know. We know P by F here, right? It's 1 by 3. Let's go back to the definition of screen. What is P by F? YF you know, YP you know. If you know this thing, obviously you can calculate YR. But this information you need to know. That is my concern here. If you don't know this information, you cannot find out YR directly from the table, because the individual mass fractions is given. But if you combine it totally, what would be the mass fraction of your desired material, that is not given.
Yes, sir, got it. We need the ratio.
Yeah, but if you need the ratio and then find out YR, it's same as replacing this one.
Yes, sir.
So there is no point of using this one.
Yes, sir. I thought of like we can, if somehow we can directly take the value from the table.
You cannot directly take, because you need this ratio. Otherwise, you cannot take because the individual streams is given, but for the entire mixture, it's not given.
Yes, sir.
Okay. Anyone else? Any question? Okay, Swastik asked me one question. Swastik, are you there? I don't know whether he's here or not, but he asked me a question which is quite valid question. So let's go to this problem. So as you can see, I have changed this column. So previously, what was it? It was the average particle size, right? The average particle size. Well, do you have the slide with you? Okay, let me go back. Yeah, this is the slide which I had shared with you. So the problem was something like this. So it was given that you have to find out the efficiency of the screen in removing the fines. So this information was given, and based on this information, I tried to construct the cumulative mass fraction table. But look at this table carefully. If I take this value, I have written that for particle size 0.59, average particle size 0.59, the cumulative mass fraction is 0.034. Now look at this table. If the information is given to you like this, is it a right information or it's not? What would be the cumulative mass fraction here for this one? Can anyone answer?
So 0.242. Oh, sorry.
Cumulative mass fraction, go from the bottom. So what is the definition of cumulative mass fraction? Cumulative mass fraction of a particle retained on screen I. What do you understand by that? Let's take cumulative mass. Let's forget about mass fraction. Cumulative mass of particle on screen I. What do you understand by that?
So all the masses below I and the mass on I, their summation.
No, not on I. It's all the particle which is below I. Smaller than, see the definition of cumulative mass fraction. Yeah, dpi is the average particle size retained. Okay, not on this one. See this table. Okay, the cumulative mass fraction. Cumulative mass fraction of this, let's take 200 mesh screen. What is the cumulative mass fraction here? 0.075. That means what? Whatever particle that you have which is smaller than the mesh number of that specific screen, that is the cumulative mass fraction of that screen. Like that's why it is 0.074. It's not 0.074 plus 0.0031. It's not like that. So make it clear, like if you are talking about IH screen and cumulative mass fraction, if I say the cumulative mass fraction of IH screen is this, that means whatever particle that is smaller than that specific screen is the cumulative mass fraction. Look at this table carefully, you will understand. 0. For mesh number 200, the screen opening size is 0.074, and the particle retained on this screen is the mass fraction of the particle is 0.0031. The particle retained on pan, which is smaller than the 200 mesh screen, is 0.0075. Now when I'm writing the cumulative mass fraction, it's 0.0075 only. It's the previous one. Now when I write it for 150, it should be summation of these two. Zero 0.0075 plus 0.0031. That will give you this value. Is that clear, or any doubt you have? If it's not clear, just tell me. Now look at this problem, the one that I had shared with you. Now what would be the cumulative mass fraction for this one? For oversize, what would be the cumulative mass fraction?
0.141.
Now for oversize?
0.
Yeah. For undersize?
0.141.
Yeah. Now what I have written here?
So we have also taken that one also.
Yeah, that's not right. I think that's why the confusion was there, because the way I defined the cumulative mass fraction, this is not what I had followed. So actually the information is partially given in the problem. This table should look like this. Now if I follow this table, right, if I follow this table, now this makes sense. Okay, let's take this one again. What would be the cumulative mass fraction now? See, if you see the problems, all this table will be given in a very jumbled form, so that to make you confused. But if the definition and the concepts are clear, you will be able to figure out. Now you tell me what is the cumulative mass fraction for this screen, the highlighted one, for oversize as well as undersize.
For oversize, it will be 0.00, and for undersize, it will be 0.141.
No, now look at this table now. It is the particle size given here minus 0.59 plus 0.42. Now if I write here particle size or the opening as 0.59, which I have written here 0.59, now this makes sense. That is what I am telling you. The average particle size here is wrong. It should be the screen opening. Yeah, this cumulative mass fraction, now it makes sense, because see this column, this row stands for, if I go back, this row stands for a screen where you have all the particle which is smaller than 0.59. Right? Is that make sense? Like if I'm talking about this screen has a mesh or an opening such that all the particles retained on this screen is smaller than 0.59. That is how it is presenting here. Yeah, any question?
Yes,
Yeah. And now if I make this cumulative mass fraction table like this is now right, this is not wrong. Because when I'm writing this as 0.59 and the mass fraction equal to 0.034, that means all the particles that is smaller than 0.59 has a mass fraction of 0.034, which is right. If it is not clear, just tell me. Anyone has any doubt, tell me, because that was a valid question and he asked me because he raised the doubt. I could understand that, okay, there was a problem in understanding, because this should represent like this. But see, if in many of the books the problem is given in such a way so that, and they solve it in their own way. So this is not the right way. That is not, this was not the right way of giving the problem. This should be the right way. And oversize also, it makes sense. When I'm writing here 0.59, then I can add these two up. Right, I can add these two and say that, okay, this is the mass fraction the cumulative mass fraction retained on this screen would be this plus this, if I write 0.59 here. Because all the particles which is smaller than 0.59 should be written here, that mass fraction. Hope it's clear to you now. Yes, any doubt? Okay. Okay, any other question from all the topics we have covered, particle characterization, screening?
Sir,
Yeah.
sir, can you explain that problem once again, which you explained just now? I mean, like just the table, how to read the table.
Yeah, how to read the table. So, what's your name?
Sir, Archishman.
Archishman. Okay, Archishman. So, but just take one row, just any row. Let's take this second row. You just tell me what you understand by all these three numbers. If I take the first column, what do you understand? If you see that minus 2.36 plus 1.56. So what do you understand?
It means that the particle size is less than 2.36 but greater than 1.65.
Okay, fine. What second column? This 2.11, what do you understand by this?
Sir, it means the mass fraction that is staying on the screen, not passing through it.
So the mass fraction of the product on oversize.
Yeah, mass fraction product or yeah, this was product for this problem, but mass fraction of oversize. Let's take it oversize. If I don't know the problem, only table. So it's the mass fraction of your oversize. What is that fraction? This is you need to understand. Like if I say that it's 21%, 21.1%. So 21.1% of the entire mixture that you get from the oversize has a particle size which is smaller than 2.36 but bigger than 1.65. Is that a right statement? Okay, Archishman, this is a fraction. This part is clear to you. This is a fraction which
Yes,
has a
sir.
specific size range, and this is the weight of that specific fraction. Weight fraction. That means the weight of that particle, that mixture, this size range divided by the entire weight. That is 21%.
Okay, sir.
Fine. That is 21% if you take the mixture from oversize.
Yes, sir.
Of the entire screen. And similarly, if you take the entire thing from the undersize, you will get this as 0.098. Now, what we are interested to find out, the particle, all the particle which is smaller than 2.36. Which is smaller than 2.36. So that would be what? Addition of all these terms?
Yes, sir.
Including this one. Because see, it is written that this is smaller than 2.36.
Yes, sir.
Got it?
Yes, sir.
So if I try to write the cumulative mass fraction for the second row, what should I write? Addition of all this including 2.11. Sorry, including 0.211. Fine?
Yes, sir.
That is what I have written here. Now, the difference with this one and the cumulative table that you have seen here is that here it's only the screen opening size given. It's not written that it's smaller than that screen. The fraction is not given, it's the mesh number is given. That's why you have to stop before that for this problem, before the previous. This is the difference between this table and that table because the way it was represented.
Excuse me, sir.
Yes.
Could you go back to the previous table that you were showing, that we were discussing?
Yeah. this one.
Sir, could you explain what the last row means? Minus 0.42 plus 2.29. What does that mean?
The particle which is smaller than 0.52 millimeter. This 2.29 number may not be right. Let me check. Should be 0.29.
All right, so that was the confusion for me. Thank you.
Yeah. Because this has to be smaller than that. Obviously, that's a valid question. What's your name?
Sir, Diya Sarkar.
Yeah. Okay. Thanks for pointing it out. So that was a typo mistake. So that creates confusion. Again, if you have this kind of confusion, that means things are in the right direction, that you understand the thing.
Excuse me, sir.
Yes.
Sir, in this table it is written, in order to remove these fines it is screened using 1.5 mm screen.
Yeah.
But sir, ideally the diameter of the aperture would vary, na? Because there would be a number of screens.
No, I think you get confused with sheaving and screen. So industrial screens may be a single screen, maybe a double screen. The second problem that we have discussed, it has only 2 screens. And this is an industrial screen which has only a single screen. So you are using a screen to separate certain particles. But what is the efficiency of that screen in separating that specific range? That we are finding out by doing the sheaving analysis of the feed stream, of the oversize, of the undersize. So you
Okay,
take, I think this is what I try to discuss on that day. So when I define the efficiency, you see you have only one screen here. This is how I define the screen effectiveness. And suppose you take this screen to be that screen which is used to solve this problem. Now you can understand, like, this is the one screen where the feed is coming, the oversize is going, the undersize is, and the sheave analysis of the oversize and undersize is given in this table. Is that clear? It's an industrial screen. So an industrial screen is specifically made for separating particle depending on that process requirement. Suppose your process required particle which has to be smaller than 1.5 millimeter or greater than 1.5 millimeter. Now you use that screen only to separate the particle which is smaller or bigger than that thing.
Okay, sir. So, sir, why we are using so much of data? We can simply
yeah, how you can do it simply?
One sieve which have a particle, which allow particle of 1.5 to pass, and the other which do not. So just 2 rows would suffice.
Yeah, but that will you take one screen which has 1.5 millimeter of opening, and then you pass the feed. And how will you calculate the efficiency of the screen? How efficient the screen is?
Okay, sir. Okay, got that.
You got my point. This is the whole thing, is to find out the efficiency. Well, if you can find out the efficiency, what's your name?
Aditya.
Aditya, in which year you are in? You are in second year or third year? I think you are in second year.
Yes, sir, second year.
Yeah, in third year you will do a experiment on vibrating screen, where you will see the difference. Like, whatever the doubt that you have, that doubt would be clear on that. Now, if you know the feed composition, if you know exactly how much particle is there in the feed, like suppose I'm giving you a 5 kg mixture where you know that out of 5 kg, 3 kgs are plus 1.5. Fine. And now you use this screen to find out the efficiency. Now, whatever weight of undersize and oversize you will get, you are in a position to comment that, okay, this is the ideal situation and this is the actual what I am getting. Ideally, the screen should have 3 kg of oversize and 2 kg of undersize, right? If the efficiency is 100%, because you know that how many of 1.5 size particle is there in the feed. And then you take the actual weight, and from this ideal and actual weight, you are in a position to comment on the efficiency. But in real life, in the feed itself, you don't know. That is also you are using a sheave. That's why doing all this analysis and everything, and sometimes this the number of the cutoff number that you wanted to use for separating the particle, that may not be standard with the sheaves. So you have to go for all these plots and all these data to find out the exact point.
Okay, sir.
Yeah. I would request you to just check this one, because we have seen here 1.5, and I have used a graph for finding out these x values. Now, instead of using this graph, do you have calculator with you? Just quickly check if you do a linear interpolation, what value you will get for 1.5. 1.5 will be somewhat here between these two values. Just quickly do a linear regression. I mean, if you don't use a graph and do a linear regression, what value of you will get?
So, what exactly we have to do?
You know the value for 1.17 and you know the value for 1.65, right? From the table itself. This is from the experiment. But what we wanted to find out, we wanted to find out the all the particle mass fraction which is smaller than or greater than 1.5 millimeter. That is what we wanted to find out, and for that we had used this graph. Remember in the last class we had used this graph. We had taken this intersection point and then we had calculated the XP and XR. Now instead, if I don't want to construct this graph, because this is somewhat in between value, right? In between value between these two, 1.65 and 1.17. 1.5 will lie in between this. So if I do a linear regression, just interpolate between these two values using a linear regression and tell me the value of XP and XR for 1.5 millimeter.
For XP 0.574.
Yeah, for XP
0.57.
Okay, let me write it down. For XP, what you are getting?
So 0.574.
574. It's exactly same as what you have got from the graph. What about XR? What? A bit loud. I couldn't able to hear you. Just come again.
Value of XR 1.65.
What is that value? Point? Can you write it in the chat box? I cannot hear you. Or anyone else who has got this value? Just do a linear regression.
It's a 0.834.
0.834. Okay. I'll tell you why I told you to do so. Okay, 0. This one. We got same as this one, XR 0.83, right? That is what you are saying. Is that correct?
So that is what I got.
Anyone else? It's a linear regression, just it's a very easy one. This is not same as 0.85.
Sir, it's 0.594.
0.594. That 0.594 is XP. That is what you are saying. It has to be between these two values. For XP and for XR, it has to be between these two values. I hope you know how to find out the how to do an interpolation between 2 points if you do a linear regression. Just if you know the value at 1.65 and 1.17, tell me the value at 1.5. We are not looking into the graph, looking into the just doing a linear interpolation. So I got two values. Yes, say that again.
0.8288. They're about 0.8.
Yeah, 0.83. So this is right. And this is what you got, 0.57 or 0.59?
Sir, I also got 0.83 for XR.
And for XP, it's 0.57 only or 0.59?
Yes, sir, 0.57.
0.57. Yes. So can you tell me, by now you look into the graph, can you tell me the reason, like why XP is same that we have received from the graph and whatever you have received from the interpolation, and XR value is different? Why?
Sir, I think because the slope is more for the XR line, which is why the value we are getting is also different.
Yes. So who is that?
Sir, Diya Sarkar.
Yeah. Okay. Diya. So whatever Diya is saying is right. See this part. This is almost a straight line, and our value lies here. So that's why whatever value of XP you are getting from graph and whatever value of that you are getting from the interpolation, both are same. But see this part, you have a curve here. So that's why it's varying. Now it might look like it's a very small variation. You check the efficiency. You check the efficiency of screen using the value XR equal to 0.83 instead of 0.85. What you will get? I have an Excel, so let me check. So if I put the XP here, XF is 0.25, XP here is 0.43, and XR I'm putting as 0.83. 0.83 means 0.17, right? 0.17, and this would come as 0.43. Yeah, so if you do it, you will get the efficiency as close to 40%. Now 40% instead of 44%. What is the percentage error? The difference is almost 4%. So percentage error is almost 10%. So you get a 10% error in your estimation if you do it with using a linear interpolation instead of a graph. So now you understand why we use a graph instead of doing an interpolation. See, this error may reduce depending on your distribution. If both falls into a linear regime, then you might get relatively less error compared to the actual one. But actual one you will always get using a graph. So that's why we go for graph always without using the linear interpolation. And graph also can give you error if the data points are very far apart. Yeah, any other doubt? Otherwise, I'll just quickly show you some of the videos of industrial screens, and then this evening would be over. Okay, so let's see some videos. The first type of industrial screen that we encounter is Giesslers. So Giesslers are mostly used to separate huge particles from that you directly receive from ore or any raw particle that you receive from nature, or by breaking it manually. So those particles is initially separated using this kind of equipment known as grizzlers. So this is how it operates. See the video. See, it has staircase type of platform, and you are putting the particle, putting the mixture on the top of it, and gradually you have opening. The smaller particle will pass through, and the bigger particle will be retained on the top of skin, which will come from one side. This is one type of industrial screen known as grizzlers, which is used. And for which type of particle and when it is used, I have written it in the slide itself. You can see this particle range and all these things I have written. Yeah, used to screen large of rocks of 25 millimeter and above size. So to separate 25 millimeter and above size, so you use this type of screens. When oversize is something you want. This is vibrating screen. This is the most popular one. I think we have seen one video of the vibrating screen. These all are like mechanical information which is given. You can go through this slide. I'll share it. Just see how it operates. This is a double-decker one, similar to the problem that we have solved. So you put the particle on the top of it. You have linear motion here, and the motion can be different also depending on what you want to separate and what is the physical nature of your particle. So this is how you separate. You can see that coarser particles are coming out from here, and the finer particles are going down. This is a vibrating screen. The vibration of the screen, direction of vibration, all will depend on the system, the process itself. So it can handle a wide variety of feet from 480 mesh to 4 mesh. It's a wide range of variety it can operate. That's why it's the most popular. I mean, this is the one which is used in most of the chemical industry also. The third one is oscillatory screen, as the name suggests. So vibrating screen falls into all the type, but this is a specific type of screen which is again mostly used to separate the very coarse particle from a mixture of coarse and fine. And it has relatively low speed oscillation compared to the vibrating screen. Mostly used to batch screen coarse material coarser than 5 to 15 millimeter. And this is how it operates. I didn't get a good video for this one. This is how it operates. So from the conveyor belt, the initial mixture is coming into the screen and it is being separated into two parts. This screen, I think it's, yeah, you'll see in front that the coarser particle are again going to a conveyor belt, and the finer particle, if you see at the bottom here somewhere, the finer particles are moving. That is another type of screen. The next movie in our list we have is reciprocating screen. It's the action of the movement of the screen that is different, and that is what becomes more specific for a specific problem. It has a reciprocating action, and the vibration and all these technical detail is given. It is used for handling chemicals, light materials, powders. All these are mostly information, so you can read it. I'll share it. Didn't I get a video from the industry itself? So this is the reciprocating action that you will see. And this reciprocating action you can get by using a shaft. A very good video, but still something to make you understand like how it operates. The gyratory screen is another popular one where the particle moves in a gyratory motion. Do you know the meaning of gyratory? Gyratory motion means what? Anyone? Any idea? It's circular or near circular kind of motion that you will see. See how it operates. Initially, the assembly part I'll move fast, and now you put the particle right on the top of the screen, and this screen moves at a gyratory motion, which results the particle to move in a near circular motion, and in each stage you have screens. So the bigger particle will go at one side of the screen and it will be taken out, and the smaller particle will go down, and again it will do using the gyratory motion. Again those particles will be taken out from one side of the next screen. It's the same phenomena that will happen in every stage, and you will get particles separated based on their size. So the next one we have is Fromel. Fromel is another type of screen which is mostly this one mostly used to separate the wastes, the bigger waste particle from the smaller one, and the construction is very coarse, so it is slightly tilted, and if you put the feed here, you will get the finer separation will happen here, and the coarser separation will happen here, and the coarsest particle, which is the biggest one, which will come out from here. Rotational speed and all this information is given. See how it operates. So you can see that it mostly used for the waste disposal. So you put the initially treated waste here, and then it will separate out in 2 or 3 fractions depending on the requirement. You can see some particles is coming out here. Yeah, and this is, you can get the big particle here, and the small particle will fall down, and there's a conveyor which will take it to the other side. Okay, this is how it operates. That's it. That is all about screening and sheaving process. So there's nothing much to discuss. So that will end up the entire sub module on screening or sheaving, whatever you say. And from next to next class, I'll start with the